But today we're going to talk about big picture, right? So not just leak detection, but what can you do with all of the data you have, with all the different sensors you have, to look at your distribution network holistically. So just a very quick intro for Digital Water. To put it simply, we are a small group of individuals that range from operators, engineers, data scientists, researchers. We all kind of came together on the basis of wanting to provide better tools for infrastructure. So because of that skill set that we have in-house, we're able to deliver novel solutions for infrastructure management, right? By integrating these applied research type angles with engineering consulting and then end-to-end product development. So hydrant.AI, as we'll talk about, is our first kind of commercial offering here. And then we'll also talk about the extension of that platform.ai in this presentation. So with that, we're going to keep it simple this time. Just really 4 things on the docket. The first one is just to make a case for holistic monitoring, right? What is it? Why do we need it? Why is it important? And then we'll get right into the meat of it. So the case study with Region of Waterloo, PVC leak detection, but with more kind of insight with other data sources. What can we see? What can we kind of glean from that after the leak? And then looking forward, right? So not just with this particular case, but let's say you're a different utility, you've got other data sources, what can you do with it? Or what's the next step, after you've kind of taken that initial plunge into holistic monitoring? And hopefully we'll leave some time here for some discussion and Q&A. Okay, so making a case. So let's start with the Doom and Gloom, right? This is the 2021 ASCE report card for drinking water infrastructure. So you can see the trend here from 1998 to 2021. It's been pretty stable up until the last 4 years where it's just skyrocketed. And those of you that are in drinking water will know that the reality of it is that it's not that great, right? We're basically sitting at a D minus, and recently we're able to get up to a C minus. So not a grade that most people would be happy with, but some of the key takeaways are, why is it so low? Why is it so poor, right? If I put another plot on the right here and we look at the trend, so what is growing exponentially over time, right? Demand. So we're expecting about 56 million additional users for water in North America over the next 20 years. Labor shortages. So, and I was just at NWWC this week, a lot of utilities were talking about the fact that they're going to be losing key people, right, over the next 5 years. Lots of retirements, lots of knowledge in those people that is going to get to go with them. So that's going to be a huge concern there. Risk and uncertainty, right? So a lot of the pipes in Canada are in fair or worse condition, which means basically in need of assessment or repair. In the US, a pipe is breaking every 2 minutes, and climate change is always adding a curveball, right? Every year, we don't know what to expect. Complexity too. So again, as we kind of move away from cast iron, ductile iron, more PVC, HDPE services, you're getting more and more utilities that operate mixed material networks. So there's just different layers of complexity that you now have to deal with that you didn't have to before. So you put that all together, and really it seems like we're stuck in a rut, right? Because you've got aging infrastructure, you have diminishing resource availability, the complexity is going up, and at the same time, the effectiveness of these existing leak detection methods, they're going down because they're really designed for what the networks were like 10, 15 years ago. They're not really future-proofed. So because of these two things, you're going to have more undetected leaks, you're going to have more unexpected breaks, more unaccounted for water overall. And when those breaks happen, you're going to replace it, most likely the PVC pipe. You're going to increase the amount of mixed material sections of your network that you have, and the circle continues, right? So there is a silver lining, because something we also have to consider is if everything is getting worse, right, why did we improve? There is still an improvement from 2017 to 2021. So if I pull that same plot up, we could also put positive things that have changed exponentially over the last few years. Technological capabilities. So with machine learning, with big data, our ability to problem solve has also increased exponentially, right? With that, the knowledge, so our understanding of these systems, we learn from the past, we learn from our mistakes. So that is all growing too, as we are forced to now confront some of these challenges in our system. Affordability of sensing. So this is a big one too, because really it's one of the kind of key motivators for this big shift in data-driven methods is if you look at between 1992, this is for an accelerometer, right? It used to cost $22 a pop in 1992, and now it's $1.40. Well, this is in 2014, so it's about 39 cents now for an accelerometer. So it's become way more accessible, which means that there's an increasing ubiquity of sensing. Everything has a sensor. There's a lot of data everywhere. You can see here just the spending, right, on IoT devices over time. This is just between 2018 and 2023, and this is exponential. So there's quite a lot of emphasis on putting sensors into places and gathering data. But the problem or the catch, right, is we don't know what to do with that data. But overall, right, I would say as a whole, we are becoming adaptable, right? We're becoming more adaptable because we have more tools. We have the potential to problem solve. We just need to know how to properly harness that. So some quotes about adaptability, right? This one never really applies to me. I'm more in this camp where I only change when I absolutely have to, but that's okay. We're at the point now where we absolutely have to change. Otherwise, we won't be able to continue operating our networks. So this is not just me making this up. In that same report card that I'm showing you here on the left, ASCE does cite the adoption of smart water technology as one of the main drivers of improvement. And again, the catch though is it's becoming available way faster than we know what to do with it. And so we're just getting into one technology, the next technology, and we're just amassing these piles and piles or silos of sensor data. And this is a report from Black and Veatch from 2021, where they went around North America and they asked a bunch of utilities, how do you feel about your data integration or your data management strategies? How do you feel about how you're utilizing your existing smart technologies? And you can see only about 5% of utilities actually have an approach, a fully integrated approach that they are satisfied with, right? 30% of the utilities just say that they're pretty much doing nothing with that data. It's just sitting in a silo. And 65% are trying, right? But they're not quite where they would like to be. On the flip side, right? Again, who's collecting data? A lot of people are collecting data. So if you add up the 50, right, the 22 and the 17 here, sorry, and the 11 here, you've got a lot of utilities that are collecting data, not really leveraging it effectively. And about 17%, which is positive, right, of utilities collecting data and are leveraging effectively. So we really want to increase this fraction, right? We want to bring it up from 17, we want to bring this up from 5%. This is really the alarming one. So again, we're simply not getting the full value out of what's already there. Now, what's getting in the way, right? Because sensors are cheap, right? We could put sensors in everything. Why isn't it working out for us? Some of the things at the technology level we have to consider, there's always going to be a trade-off. So when it comes to monitoring devices for drinking water, for example, when you talk about leak detection or leak localization, right? You're always riding the line between, do I want more coverage or range, or do I want to be more precise? Do I want to narrow down where that leak is? The farther apart you put your sensors, the more coverage you get, but then the less accurate you can be when it comes to pinpointing the leaks. On top of that, you also have this balance of your resource or time savings. So if you want to know more detail, if I want to know why something happened or where specifically what process may have caused the break to occur, right, I need to invest time and resources into that. So the more that I want to know, the less time and resources I'm going to have available to me. So those two together basically mean that you can't have your cake and eat it too, right? And that's the reality of it right now. Again, things will always change as technology advances. At the utility level, this translates further to, again, exponential, right? If you want the maximum coverage, you're going to have to pay. And it's going to be way more than what pretty much any utility right now can feasibly pay. It's just not realistic. Also, this piece, if you want to understand more about your network or you want to get to a certain level of it, it's going to require more time and resources than you actually have. And those two together really lead to, as you add more and more of these solutions, more sensors, you end up with just more work, more problems, frustrations, and perhaps doubts or skepticism that these things do anything at all for you. So that's kind of the barrier to actually unlocking a lot of the potential behind the technologies that we already have in place. So what's the solution? I mean, obviously based on the name of the webinar, right? It's going to be holistic monitoring, AKA the art of having your cake and eating it too. And I really do think that this is kind of a nice compromise that we can have in the beginning, at least while we're working towards more efficient IoT, better integration out of the box. This is really the way forward for us in the next 5 to 10 years to be able to do more with what we have available. So what it is pretty simple, right? You're just taking different technologies that you have or data sources, and you're using them together to inform decision making. But things like you have pipe condition, for example, maybe you did an assessment with a consultant. You've got a database for that. You have GIS, you've got leak detection, you've got pressure, AMI. All of these, again, are separate siloed data sources for most utilities. And the reason why we need to use holistic monitoring is, again, all of those things we mentioned just in the previous slide. You can't really have the coverage you need with one solution. There's no one size fits all solution. Different technologies are going to be better suited for different tasks. The cost and resource constraints. So different technologies, for example, like a manual survey technology might be really good at pinpointing precisely where a leak is, but you can't always go out. You don't always have someone to go out and do that survey. So it's really important to kind of mix and match and make the most of what you have. And the catch is, again, this requires that integration, right? And this is not something that's prioritized by most providers right now in water. They want to keep you in a silo, and this is just how it is across all tech, right? Think about Apple versus Android. This is just kind of the way it goes. So maybe a more tangible example here, right? Let's say that you've got leak detection. So we detect the leak. And that tells you, I might have a leak. So in this axis, we've got confidence, or maybe the amount of actionable insights you're getting from your data and the level of understanding you have of the problem. Let's say beyond that, though, you want to increase that confidence. So you check to see maybe, do I see it in my pressure, my flow? Do I have other machine learning models that are running on other data sources that might be able to elaborate on what the acoustics are seeing? Maybe you see it in the flow, right? And that would say, okay, the increase in minimum overnight flow further confirms the fact that I've got a leak. Maybe you look at the SCADA data, the pressure data, and say, okay, that actually shows me some correlation, some causation. Maybe there's a root cause there. We could prevent it in the future. And then you can also look at, okay, I've got a leak, but I've got 10 leaks. So how bad is this one? So if you look at querying your GIS or digital twin, right, you might be able to figure out this leak is or isn't a high priority, or if I were to repair it today, how much money would I save? So these are just kind of the ways that you can build on, one technology with the other ones and build on that level of confidence and understanding that you want to get to without having to pay extra. So where does hydrant.AI fit in? Leak detection. The name hydrant.AI doesn't really imply that we do much with other data sources. And how we've kind of gone about that is we're looking at platform.ai, right? So we know for hydrant.ai, what we do is we provide monitoring for any network. We take a regular hydrant, we can turn it into a smart hydrant, and we've designed it to be as flexible as possible, meaning that with our sensing technology, we can deploy in any material. So it doesn't matter if you're mixed material, it's designed for that. It could be PVC, it could be iron, no problem, right? The autonomous AI is really the driver behind the platform AI piece. So what we've also worked on is trying to come up with machine learning models that don't rely on GIS, that don't rely on historical data. You just plug it in and you're able to detect and locate leaks. You're able to monitor pressure without any input. So that same basis is what's used for platform.ai, which is really just taking that autonomous AI and saying, you can apply this to any data source that you already have. So let's say you've got flow rates, right? Flow data. You can apply that and monitor for flow anomalies. Pressure, you can learn pressure patterns, right? And monitor for pressure anomalies. And this really lets you take that and turn any existing data source that you have into a smart sensor, and then get the decision support that you need from that through holistic monitoring. Okay, so let's get into kind of the interesting part is the case study. So Region of Waterloo, they have been partnering with us over the last about a year or so, first starting off with a leak detection pilot and then continuing to build out on a program to tackle unaccounted for water in air. So air is the largest region they have or largest community they have in North Dumfries. The region itself services approximately, should be 600,000 people, and they do water supply and treatment as well as wastewater treatment. So air is right here, if you're familiar with the area. And a little bit of the story so far for them. So you can see they have a lot of PVC. They have HDPE services. They started off with this multifaceted leak detection program in 2015, and they have a history of high water loss here. They actually inherited this area from a different utility. And some of those key events are in the timeline. You can see they did satellite leak detection at some point. They did acoustic loggers. They tried service investigations, step testing, DMAs, telelogs to log flow. And then the future projects we're kind of part of is the acoustic leak detection and being able to see, what can they build on with those existing data sources that they had previously installed. So this kind of happened in a couple different phases. The first being a pilot, which took place for about 6 months in Piper area, where we installed 10 of these devices. Then we moved on to expand the area to the right of that, which is central, which is where the distribution is located, the treatment plant. And then the overall just looks like this. So this is Piper down here. This is central. And phase 3 is what's the next step, right? So to be determined when we're going to start that, but the addition of decision support. So this just gives you some rough numbers of the coverage that they have. They're about 44% of their mains covered at this point, with, I believe, 2 more DMAs to deploy in. And I'm not going to spend too much time on this here, but so we had a bunch of different leaks that were some confirmed, meaning they were detected, repaired, and some are still suspected, so ongoing. And what I want to focus on here is the key questions when it comes to holistic is when you have multiple small service leaks, is there a way that we can quantify and decide how to prioritize what and when to repair? Can we also quantify the impacts of our actions? So if I wanted to go out and fix it 2 weeks in advance, and I need to convince somebody that that's a good idea, right? What can I tell them from the data? Also, this is very important too. At the engineer level, right, there is usually some level of enthusiasm towards trying new things and different new shiny tools in terms of AI. The operators are really concerned about keeping things going and minimizing losses and really just, if something ain't broke, don't fix it, right? So the way that they do leak detection, it's going to be very hard to take up more of their time trying out a different technology, having that technology not work out the way that it's supposed to work. It's very hard to convince people to change the way that they do something. So you need to find a way to build that confidence in a solution. So we're going to focus in on this leak here, this LP1 leak. I'll just walk through now what this leak would look like with all the different data sources we have available. So this leak started, didn't start in November. We started acoustic data collection in mid-November. And the first thing we thought was, you might have a leak near hydrants 8 and 9 here. So that's what the acoustic AI sees. There's a location. And then we could also determine that this was a pre-existing leak. So this is just showing this purple band is kind of one of the signatures that the AI looks for. So these are the different frequencies we're hearing in our data. And you can see that from the start of that collection at 11:15, there's already this purple band. And once they repair this leak in the future in January, that band disappears. So this is a pre-existing leak. The 2 sources are already informing this decision. And then we can look at leak energy, right? So we can try to capture, is that leak growing? Is it staying the same? And we can see again from the 15th of November to about the end of December, there's not much change, right? Very, very minor change. And then it starts to really kick up in December and then into January. So now we can look at pressure, right? And these are the pressure data for the area. And you can see this is the pressure.ai. It's picking up some anomalies, one at the 16th or 17th of November, one around the 25th, and then this one here, right, around November 30th to December 2nd. And that happens to coincide with when this growth starts to change. The leak is no longer just stagnant, it's starting to grow. So again, it's just coincidence at this point, but we can maybe look deeper later on to see if there's a correlation or there's causation. Okay, finally, right at the end, again, we can use that leak growth to tell us that, okay, it's changing exponentially now, we should probably go and fix it. And then we could also look at flow. So at this point, it becomes evident in the flow data that, yeah, I'm seeing the minimum overnight flow is drastically increasing over the last few days. That confirms it, right? So it gets called in, they repair it, and then you can see in the flow data, there's a quantifiable drop, and I'll show that on the next slide. But the key thing I mentioned here is that it was called in, right? This is not a leak that the region went out and said, hey guys, dig here. Yes, it was in the location that the AI said it was in. But again, it's the very first leak that we ever looked at with them. So there's not going to be the confidence on both sides of it. On the engineering side, is on the operations side, that this AI is doing what it says it does. So it's very important that this gets called in, repaired, and then we can look back and say, okay, well, yeah, everything that we were talking about, everything that we had kind of discussed beforehand and in the weeks leading up to this, that all checks out. And that helps build that confidence over time. So you can see that energy after they do the repair, that green line, it's basically zero. Okay, so this is that leak energy, right? So if I take that leak energy and I've kind of grayed out all the other leaks that we've looked at with them right now and just focus on LP1, this is the TELOG data, and this is the 7-day rolling average, the overnight minimum flows. So Piper is the yellow here, and you can see where the repair happens. Remember, this is 7-day rolling average, so there's going to be a slight delay. You can see that drop. Here's that increase just a few days prior to that. So that's when they really start seeing it. And you can see prior to that, there was no change in the flow. So that's why it was important for the acoustic to come in and be able to pick that leak out early, make them aware of it, right? Once it hits this point, it's evident that that is indeed going to be a leak. It's going to be a break. It breaks, you do the repair. And now you can take this and you can quantify what's that worth, right? You can actually use this and compute, how much water was lost. Again, knowing the pressure there, knowing the flows. Here are kind of the other repairs that were done, right? And you can see where they line up. So some of these, the P's, that means Piper, right? These are done in Piper, and you can see the drops that happen after each one. So LP3, when it was repaired, not a huge drop, right? When LP2 was repaired, though, that was quite a significant drop in the flow. And this is also just showing that it's a never-ending battle, right? So you've kind of got, you fix it, you're back to a certain baseline, and then it starts to increase again. You get new leaks, you fix it, and then it starts again. So at least it lets you stay on top of it, right? That's kind of the important part. And then as you build an understanding from this over time of what might be causing these leaks, that's how you go from, reactive to preventative. And these are a couple here for C, which is central. You can see here the blue, right? Where really the big impacts happen. So some of the massive leaks that were fixed in central line up pretty well here. Okay, so looking forward, right? This is all good, but what's it worth? So if we look at it from a decision support perspective, right, that's that service leak at the time of the repair. A couple of things we can say. So I've used a different color here for the different data sources just to make it kind of easier to see what's being used in what. But we take the flow, we take the pressure data, we can estimate then the average flow rate of the leak itself. And we could find it to be between 5 to 15 gallons per minute, depending on what stage of that leak it was. So 5 being kind of that dormant, pre-existing state, and then 15 being closer to the end of it before it was surfacing. And then we can also look at that average flow rate. We could look at billing or consumption data, and we can estimate the water loss. So that period where we looked at between 18th of November to 17th of January, that month, 2 months, sorry, it's about 1 million gallons. And that's about $17,000 in lost revenue. Now, not huge objectively in terms of utilities, because again, where we are, water's pretty cheap, right? With the acoustics and the leak fingerprinting, we could determine that that leak was pre-existing. So now the savings go beyond, or they precede the 18th of November, right? Depending on how many months you think that leak was there prior to, which is something we won't be able to know. All we know is that that leak was there beforehand. And if you'd done a leak survey in the past, you could see, was it picked up? Was it not picked up? Who knows how long it was sitting there? But every leak like that is going to potentially be costing you $3,600 a month. And after we, spend some time in one area, we can get an idea of how many of these types of leaks you might have per kilometer per mile of pipe. Okay, we can also take that case study we just did and try to find deeper correlations between the pressure, between SCADA and distribution and leak growth, right? Is it something we're doing at the treatment plant that is causing leaks to grow over time? Or is it the way that we're, maybe isolating sections for capital projects that are causing some imbalances in other parts of our system? And this also helps you build that system understanding. So this is really working for long term. I want to just reduce the amount of leaks that I have in general, not just be able to detect them after the fact. You can also take this down, you can approach these numbers from different angles. It's if you know the amount of water that's being lost, you know the amount of energy it takes to produce that water. You can also measure it in terms of GHGs, right? So for all these leaks that are spitting out $3,600 worth of water into the ground, how many trees would I need to plant to offset the CO2? And those are different ways to look at it. Very easy to get that once you have this level of insight. Another important part is it supports KPIs for regulatory reporting, right? And this is more in the US at the moment, but I'm sure it'll make its way up here. But you have to be able to answer in the US if you are above a certain percentage of unaccounted for water, you need to show a clear plan and you need to show and demonstrate that you're hitting certain KPIs to bring yourself below that threshold again. So this lets you have a dashboard, a calculation set up so that when I fix a leak, I can then see directly from the flow, right, what was the impact of that action? And it really makes it easier to show in regulatory reporting. And lastly, you can build a stronger case for ROI, right? So if you now want to purchase more technology of some sort, if you're able to tie it in with the other technologies, you're able to then see, what is it actually saving me in the long term? Is it making my job easier? Is it actually helping us in terms of capital expenditure, in terms of replacements and asset management? So that's kind of just with what we have so far, right? And where we're moving towards with Region and other utilities is, okay, let's take some of that data and build beyond leak detection. So one of the things is looking at possible next steps, automated water balances. It's a lot of utilities use the M36 water balance as kind of a model for seeing where they are, benchmarking where they are in terms of unaccounted for water. And one of the main missing pieces right now is you need the meter data and you need the flow data and you need district metered areas, obviously. That meter data for a lot of utilities is still manually read. It's read, by a person every 4 months. And so you have a long gaps in between that data. So what we've been able to do is, again, apply that autonomous AI. We could take that historical data, we can fit distributions of that historical data. So for each meter, we understand what the meter read is going to be in each month. And we also know the relationships between that meter and the next meter. So maybe if one of them gets read, that lets us calibrate the surrounding meters. From that, we can then estimate, freely predict future missing meter reads. So now instead of having to wait 4 months, we've effectively been able to convert this manually, discretely read meter read data into something that you can continuously provide. So we can now get a daily estimate for the, say, average total consumption for a DMA. And then we can take that consumption, we can also estimate how much water is being pumped in, right? How much water is leaving, so we can get the net flows. We can pump in that SCADA data. We can estimate the minimum overnight inflow, which is used to calculate real losses. And all this together lets you then find, what is the total amount of water that I'm losing every day. So now you can have a daily estimate, a sample dashboard of that, right? So you got your hourly rolling average flow rate, your minimum overnight inflows, your estimated daily NRW, and your average total daily consumption.